Chapter 23 Behavior of Clocks and Measuring Rods on a Rotating Body of Reference. Hitherto, I have purposely refrained from speaking about the physical interpretation of space and time data in the case of the general theory of relativity. As a consequence, I am guilty of a certain slovenliness of treatment, which, as we know from the special theory of relativity, is far from being unimportant and pardonable. It is now high time that we remedy this defect. But I would mention at the outset that this matter lays no small claims on the patience and on the power of abstraction of the reader. We start off again from quite special cases, which we have frequently used before. Let us consider a space-time domain in which no gravitational field exists relative to a reference body K, whose state of motion has been suitably chosen. K is then a Galilean reference body, as regards the domain considered, and the results of the special theory of relativity hold relative to K. Let us suppose the same domain referred to a second body of reference, K prime, which is rotating uniformly with respect to K. In order to fix our ideas, we shall imagine K prime to be in the form of a plane circular disk, which rotates uniformly in its own plane about its center. An observer who is sitting eccentrically on the disk K prime is sensible of a force which acts outwards in a radial direction, and which would be interpreted as an effect of inertia, centrifugal force, by an observer who was at rest with respect to the original reference body K. But the observer on the disk may regard his disk as a reference body which is at rest. On the basis of the general principle of relativity, he is justified in doing this. The force acting on himself, and in fact on all other bodies which are at rest relative to the disk, he regards as the effect of a gravitational field. Nevertheless, the space distribution of this gravitational field is of a kind that would not be possible on Newton's theory of gravitation. Note, the field disappears at the center of the disk and increases proportionally to the distance from the center as we proceed outwards. End of note. But since the observer believes in the general theory of relativity, this does not disturb him. He is quite in the right when he believes that a general law of gravitation can be formulated, a law which not only explains the motion of the stars correctly, but also the field of force experienced by himself. The observer performs experiments on his circular disk with clocks and measuring rods. In doing so, it is his intention to arrive at exact definitions for the signification of time and space data with reference to the circular disk K prime. These definitions being based on his observations. What will be his experience in this enterprise? To start with, he places one of two identically constructed clocks at the center of the circular disk and the other on the edge of the disk, so that they are at rest relative to it. We now ask ourselves whether both clocks go at the same rate from the standpoint of the non-rotating Galilean reference body K. As judged from this body, the clock at the center of the disk has no velocity, whereas the clock at the edge of the disk is in motion relative to K, in consequence of the rotation. According to a result obtained in section 12, it follows that the latter clock goes at a rate permanently slower than that of the clock at the center of the circular disk, as observed from K. It is obvious that the same effect would be noted by an observer whom we will imagine sitting alongside his clock at the center of the circular disk. Thus, on our circular disk, or to make the case more general, in every gravitational field, a clock will go more quickly or less quickly according to the position in which the clock is situated at rest. For this reason, it is not possible to obtain a reasonable definition of time with the aid of clocks which are arranged at rest with respect to the body of reference. A similar difficulty presents itself when we attempt to apply our earlier definition of simultaneity in such a case, but I do not wish to go any further into this question. Moreover, at this stage, the definition of the space coordinates also presents unsurmountable difficulties. If the observer applies his standard measuring rod, a rod which is short as compared with the radius of the disk, tangentially to the edge of the disk, then, as judged from the Galilean system, the length of this rod will be less than 1, since, according to section 12, moving bodies suffer a shortening in the direction of the motion. On the other hand, the measuring rod will not experience a shortening in length, as judged from K, if it is applied to the disk in the direction of the radius. If then the observer first measure the circumference of the disk with his measuring rod and then the diameter of the disk, on dividing the one by the other, he will not obtain the familiar number pi equals 3.14 and so on, but a larger number. Whereas, of course, for a disk which is at rest with respect to K, this operation would yield pi exactly. Note, throughout this consideration, we have to use the Galilean non-rotating system K as reference body, since we may only assume the validity of the results of the special theory of relativity relative to K. Relative to K prime, a gravitational field prevails. End of note. This proves that the propositions of Euclidean geometry cannot hold exactly on the rotating disk, nor in general in a gravitational field. At least, if we attribute the length 1 to the rod in all positions and in every orientation. Hence, the idea of a straight line also loses its meaning. We are therefore not in a position to define exactly the coordinates x, y, z relative to the disk by means of the method used in discussing the special theory. And as long as the coordinates and times of events have not been defined, we cannot assign an exact meaning to the natural laws in which these occur. Thus, all our previous conclusions based on general relativity would appear to be called in question. In reality, we must make a subtle detour in order to be able to apply the postulate of general relativity exactly. I shall prepare the reader for this in the following paragraphs.